Am I audible?
Yes, ma'am.
Okay. Please ask your friends to join the class. Okay. Am I audible? Okay, okay, okay. Let me share the screen, okay?
In this lecture, we are going to cover the static
This audio and video is okay?
beams. What do I mean by static analysis? I mean the process of calculating forces in a beam using the static equilibrium equations only. No dynamic forces are considered. For two-dimensional systems, these equations are. And what do I mean by a determinate beam? This is a beam which we can analyze solely using the equilibrium equations. For example, this is a statically determinate beam, whereas this is not. What is the difference between the two?
Are you able to
This
see the
beam has
screen?
three support reactions
Okay,
only.
okay.
They
Okay,
can be
I'll
calculated
start from
using
the
the
beginning, okay?
equilibrium equations. On the
So today we'll see beam analysis, but beam analysis under that statically determinate. Then we'll see the shear force and bending moment diagrams, okay? So let's start from the beginning.
In this lecture, we are going to cover the static analysis of determinate beams. What do I mean by static analysis? I mean the process of calculating forces in a beam using the static equilibrium equations only. No dynamic forces are considered. For two-dimensional systems, these equations are. And what do I mean by a determinate beam? This is a beam which we can analyze solely using the equilibrium equations. For example, this is a statically determinate beam, whereas this is not. What is the difference between the two? This beam has three support reactions only. They can be calculated using the equilibrium equations. On the other hand, this beam has four unknown reaction forces, so the three equations are not sufficient for determining the unknowns. We call this a statically indeterminate beam. This lecture focuses on the static analysis of determinate beams only. A statically determinate beam could be drawn this way. We call this a simply supported beam. We could also have a variation of it, a simply supported beam with an overhang. A cantilever is another type of statically determinate beam. A beam with one or more internal hinges could also be statically determinate. This beam has one internal hinge. And here is an example of a determinate beam with two internal hinges. Before we embark on the analysis of these beams, let's talk about their supports. Three types of idealized supports are generally used in beams: roller support, pin support, and fixed support. But how do these supports differ from each other? They differ in the ways they move in response to forces internal to the beam. The roller support can move in two ways. It can rotate in order to prevent a bending moment to develop at the joint, and if necessary, it rolls in the direction parallel to its surface of contact so that it can avoid resisting a force in the same direction. But the support does not move when the force is normal to its contact surface. When such a force is present, a reaction force develops at the base of the support, per Newton's third law. Similar to the roller, the pin support can rotate, preventing a moment reaction to develop. But the support does resist both a horizontal force and a vertical force. A pin does not move in either x or y direction. The fixed support neither moves nor rotates. Therefore, it provides three support reactions: a force in the x direction, a force in the y direction, and a bending moment. Now that we know how many reaction forces are associated with each support type, let's begin the analysis. Generally speaking, static analysis of beams involves calculating support reactions, internal forces, stresses, and deflections. Here, however, we are going to focus on calculating support reactions.
So in the beam analysis, what we do, we calculate the support reactions, we calculate internal forces, which is considered as shear force and moment, and we calculate stresses on those beams, and we calculate deflection. Okay. So during the beam analysis, what we do, we used to find out the support reactions, internal forces, like internal forces will be shear force and bending moment, and we used to calculate the stresses and the slope and deflection. Okay, these are different parts of beam analysis. So let's see one by one.
Only. More specifically, we want to determine the reaction forces in a simply supported beam and a cantilever beam, subjected to a concentrated or a distributed load. Let's start with the simply supported beam with an overhang. The beam carries a concentrated load of 1 kilonewton. What are the reaction forces at the pin and roller supports? We start by drawing the free body diagram for the beam. There is one reaction force at the roller and two reaction forces at the pin. Since the reactions are not known, we can assume their directions. Each force can be shown having a positive or a negative direction. For the sake of consistency, we assume them to be positive per our sign convention. Now we write the three equilibrium equations. Solving the last equation, we get the second equation gives us AY, and from the first equation, we can see that AX is 0. So, here are the results, the non-zero support reactions. Since AY came out negative, we know that the actual direction of the force is the opposite of the assumed direction. So, we flip the force direction and change its magnitude from negative to positive 0.5, meaning the force is acting downward with a magnitude of 0.5 kilonewton. Now let's replace the concentrated load with a distributed load. Say we have 3 rows of sandbags stacked on top of each other, like this. We estimate the weight per unit length to be 1/2 of a kilonewton. Since the load is rectangular in shape, we can model it as a uniformly distributed load. We show this using a rectangle like this. Let's draw the free body diagram for the beam. For the purpose of calculating the support reactions, we can replace the distributed load with its equivalent concentrated load. The magnitude of this concentrated load equals to the area of the rectangle. The position of the load is at the geometric center of the rectangle, which in this case is the midpoint of the beam. Again, we have 3 support reactions here, 2 reactions at A and 1 reaction at B. Here are the 3 equilibrium equations. Solving the third equation for By, we get, then the second equation gives us Ay. And we know Ax is 0 from the first equation. Here are the results. Or, now consider a cantilever beam carrying a concentrated load of 1.5 kilonewton. We wish to calculate the reactions at the fixed support. Here is the free body diagram for the beam. And here are the 3 equilibrium equations. Solving them for the unknown forces, we get. So, there is an upward reaction force of 1.5 kilonewton and a counterclockwise moment of 9 kilonewton meters at the fixed support. Now consider the case that the cantilever beam is holding a bunch of sandbags, the shape of which can be viewed as a triangle. Suppose we have measured the intensity of the triangular distributed load to be 2 kilonewtons per meter. We wish to calculate the support reactions for the beam. On the free body diagram, we are going to replace the distributed load with its equivalent concentrated load. The magnitude of the load is equal to the area of the triangle, which has a height of 2 and a base of 7. This gives us a total force of 7 kilonewtons. The load is placed at the geometric center of the triangle, which is 4.67 meters away from the left end of the beam. The diagram shows the support reactions at A as unknown forces. Here are the equilibrium equations. And here is the solution. There is an upward reaction force of 7 kilonewtons and a counterclockwise moment of 32.7 kilonewton meters at A. See if you can analyze the following statically determinate beams, each having at least one internal hinge.
So try to solve these kind of problems, okay? 1, 2, and 3. Take a screenshot and solve by yourself these kind of beams, okay? Let me share another screen.
Shear and moment in beams. When a properly supported beam is subjected to
Are you able to see
loads,
the
it is going to
see the screen?
deflect.
Screen is visible.
Although such a deflection may not be visible, it does cause internal forces to develop in the member. Take segment A, B of this simply supported beam. Under the applied load, the
Screen is
segment
visible.
deflects downward.
Okay, okay. I'll start from the beginning. Huh?
Shear and moment in beams. When a properly supported beam is subjected to loads, it is going to deflect. Although such a deflection may not be visible, it does cause internal forces to develop in the member. Take segment A, B of this simply supported beam. Under the applied load, the segment deflects downward. This deflection compresses the top part of the segment while stretching its bottom part. We say the top part is in compression and the bottom part is in tension. Imagine the beam consists of an infinite number of long fibers. All the fibers along the top part of the segment are in compression, although to a different degree, and the fibers along the bottom part are in tension. The fiber that lies between the top and the bottom group, however, is neither in compression nor in tension. I have shown that fiber in color green. Suppose we straightened the fibers without changing their new lengths. Then we can see that the top fiber is the shortest and the bottom fiber is the longest in the section. And of course, the middle fiber experiences no change in its length. We refer to the axis that passes through that middle fiber as neutral axis. The topmost fiber, since it is the shortest, can be viewed as having the largest compressive force acting on it, and the bottom fiber, since it is the longest, then must be subjected to the largest tensile force. The force acting on each of the remaining fibers varies based on its position relative to the top and bottom fibers. It is important to note that the fiber along the neutral axis carries no force. Here are the forces present at the two ends of the segment. From the direction of the forces, it should be obvious that they want to cause a rotation. These forces want to turn the right vertical plane in the counterclockwise direction, and these forces want to turn the left vertical plane in the clockwise direction. We can argue that this rotational tendency is being caused by an internal force, which we call a bending moment. Let's refer to this compression force as P1 and denote its distance from the neutral axis as D1. We can do the same for the other forces. So, associated with each force is a corresponding distance from the neutral axis. The bending moment is defined as the sum of the product of each force and its distance from the neutral axis. So we have a clockwise bending moment at the left end of the beam segment and the counterclockwise moment at the right end of the segment. This pair is referred to as a positive bending moment, since they associated with compression along the top fiber and tension along the bottom fiber in the segment. A negative pair of bending moments acts in reverse. It causes tension along the top and compression along the bottom fiber of the segment. Now that we have a better understanding of the nature of bending moment in beams, let's see how we can calculate it. Consider a simply supported beam subjected to the weight of a person. Assuming he is standing at the midpoint of the beam, we wish to determine bending moment in the beam 1 meter away from the right support, at point C. We start by determining the beam's support reactions. Here is the free body diagram showing 3 unknown forces. There are 2 reaction forces at the pin and 1 reaction force at the roller. We write 3 equilibrium equations, then solve them for the unknowns. Having determined the reaction forces, we are now in the position to calculate bending moment at C. To do so, we cut the beam at C, separating it into a left segment and a right segment. This exposes the internal bending moment at C. The moment appears in both segments. The one for the right segment is drawn in the clockwise direction, and the one for the left segment is shown in the counterclockwise direction. Note that each of these internal moments tends to compress the top part of the beam near the cut point. Hence, it is considered to be acting in the positive direction. We can calculate this unknown bending moment using either the left or the right segment of the beam. To determine the moment, we simply apply the moment equilibrium equation to point C. For the left segment, the equation is, solving it for mc, we get bending moment has a unit of force times length. So here we have the moment expressed in kilonewton meters. Of course, we could have calculated the moment using the right segment of the beam, which would have given us the same value for mc. Let's calculate bending moment at another point, say point D. We start by cutting the beam at D. Draw the free body diagram for either the left or the right segment of the beam. Then write and solve the moment equilibrium equation in order to determine the internal moment. In addition to bending moment, beams carry another internal force. We call it the shear force. It is a force parallel to the cross-section of the beam. To see why shear develops in a typical beam, consider segment CD. It is subjected to distinct moments at its left and right ends. This pair of moments causes compression in the top fibers and tension in the bottom fibers of the segment. Let's show the compression and tension forces acting on the fibers this way. Since the left end moment is larger than the right end moment, compression and tension forces at the left end are going to be larger than their counterparts at the right end. I'm going to refer to the total compressive force at the left side as Q, and use R for the total.
Okay, let me share once again. Okay, maybe there were some error network issues. Till then, all of you write your roll numbers in the chat box. Please, all of you write your roll numbers in the chat box. I call out the roll numbers. Please check once. Okay. 81, 81, 92, 107, 110, 62, 97, 76, 70, 120, 82, 109, 88, 71, 99, 93, 67, 94, 91, 78, 84, 113, 112, 90, 95, 103, 72, 63, 61, 86, 52, 54, 118, 74, 102. Okay. When in this meeting, you join in the next meeting after 2 minutes, 3 minutes. Okay. We'll continue the class in that session, the next session.